So I'm recording this video on the road, and I'm coming off a week where I've been really sick. So sorry if the camera angles aren't perfect. I've done the best I can, and also sorry if my voice is a little bit scratchy. But thankfully, this is a really short video. It's basically an extension of video 3, except instead of just applying it to a one-sided equation, the original explicit differencing method that we had used, we're applying it to a two-sided equation, the Crank-Nicholson method, and we're going to be showing that for any time step or any position step, you're going to end up with a valid solution, a stable solution. So if you recall from the last video, the left-hand side of the Crank-Nicholson equation is really similar to this equation here, except we have this block of terms also attached to the left-hand side. And in the left-hand side equation, this first term and this last term are negative. The other difference is instead of using r, we're going to be using u, which is alpha delta t over 2 delta x squared. So those are the only two differences. So I'm just going to jump right into the solution part, rewrite this in terms of u in cosine. But if you need a refresher on how to do that, I'd recommend going back to video 3. So we have on the left-hand side, at the next time step, we're going to be having, again, the first and the third terms are negative, and this was initially positive, so the left-hand side, this will be a minus. We're going to have 1 minus 2u minus 2u cosine of k delta x. And this is going to be the left-hand side. And then on the right-hand side, we're going to have t, j, comma, n, for the current position and time step. We're going to have 1 minus 2u again, plus 2u cosine of k delta x. Right, and then the next step is just to divide across. So I have tj comma n plus 1. It's going to be equal to tj comma n. And then we'll have 1 minus 2u plus 2u cosine of k delta x. And on the bottom we'll have 1 minus 2u minus 2u cosine of k delta x. Alright, from there we just have to shift things around a bit. Tj comma n plus, tj comma n. And we'll have on the top, let's factor out this 2u, so we'll have 1 minus 2u, and then 1 minus cosine k delta x. And on the bottom, can probably do a better line than that. We'll have 1 minus 2u, and then we'll have 1 plus cosine of k delta x. Alright, and this is really similar form to the previous video, or video 3 I should say, where this term can also be rewritten. T, j, comma, n. We only have to rewrite it on either the top or the bottom. I think I'm going to rewrite it on the... We'll rewrite it on the bottom. So on the top I'll have 1 minus 2u, 1 minus cosine k delta x. So yeah, this arrow is actually useful. We're basically going to be converting the bottom to match this expression here. And then on the bottom we'll have 1 plus 2u, 1 minus cosine of k delta x. Alright, and then you might recall from video 3 that or you might just recall, for the cosine expression, it's always going to be less than or equal to 1 and greater than or equal to negative 1. So in this case, 1 minus a number that's always less than 1 is always going to be a positive number. So these two parts of the expression are going to both be positive no matter what. And this 2u, u equals alpha delta t to delta x squared. All these terms that are being put into u are all positive as well. So no matter what, we're going to be having a positive number that can describe this expression, this part of the expression, both on the top and the bottom. So we're just going to rewrite this as omega instead of the 2u 1 minus cosine k delta x, or 2u 1 minus, the 2u 1 minus cosine k delta x. And I'll just rewrite this now. And on the top we'll have 1 minus omega, and on the bottom we'll have 1 plus omega. So now it's just pretty simple basic limits. Any number, 1 minus a positive number will always be less than 1, and 1 plus a positive number will always be greater than 1. And again, this is always a positive number. And so really a way that I'd like to write this that isn't accurate mathematically is just, the top will always be less than or equal to 1. So if omega is 0, the top will be 1, the bottom will be 1, and our entire stability expression, I should say, is going to be equal to 1, but it'll never exceed 1. So the top will always be less than or equal to 1, and the bottom will always be greater than or equal to 1. So since the goal for stability is to have this part of the expression never be greater than 1 or less than negative 1, in this case we know that it will always fall between negative 1 and positive 1 because we're dividing a greater number on top or a smaller number on top by a greater number on the bottom, and it's stable for any value that you may put into this term here, this term u, or any value that you may put into this cosine k delta x. So for any time step or any position step, it's going to be stable.